Graph Theory Class 1, Video 3. In this video we're going to do a couple more examples of graphs occurring in the real world. In the previous video we did a bunch of examples where the objects of the graph were people, Alice, Bob, Charles, David and Eve, and we looked at relations such as friendship, fancying and dislike. This time the objects in our graphs are going to be geographic locations. So let's begin. This first example, I want the objects to be local towns and the relationship to be length of the road between them. So if I put Bloomington right in the middle, then I can add other local towns around it. So I can put Clear Creek down here and I'll draw an edge and I'll label it with a 1 because the road which this edge represents is 1 mile long. Maybe I'll put Ellettsville up here. Okay, and apparently there are 2 roads to Ellettsville from Bloomington. One of them is 8 miles and one of them is 9 miles long. Okay, and these roads, they're two-way roads, right? All of these roads are 2 ways, so I don't need to add arrows to this. Maybe I'll put Unionsville up here. And apparently the road to Unionsville is 11 miles. And maybe I'll put Nashville over here. Okay. And apparently there's a road from Bloomington to Nashville, which is 15 miles. And there are 2 roads from Unionsville to Nashville. One of them's 16 and one of them is 20. Okay. So this is a graph which represents geographic data. It represents towns and the length of roads connecting the towns. One important thing to note about this type of graph is abstractly it doesn't matter how I lay out the graph. I've laid it out so it's reminiscent of how the towns are actually located relative to one another. Like Ellettsville is to the northwest of Bloomington and Nashville is to the northeast, but there's no reason why I need to do this. I can just do like any weird thing I want, okay? And in terms of graph theory, it's still the same. There's still an edge joining Bloomington to Nashville. It's just messier, but the mathematical content is exactly the same. It doesn't matter that I put Clear Creek down the bottom. I could have put Clear Creek anywhere, okay? And you can imagine examples like this coming up in the real world, like every time you use a GPS or you ask Google Maps for directions somewhere. It does calculations using graphs like this. It needs to know the quickest way of getting from Clear Creek to Nashville. Well, it will look at all the different ways of joining these 2 things up. And the computer will represent that data as a graph. Okay? So you can imagine there's all sorts of different applications for graphs which represent this sort of data. Let's move on to another example. So in this example, the objects are going to be states of New England, and the relationship is they share a border. So what I mean by this is 2 vertices have an edge joining them if the states they represent share a border. So the easiest way to draw this graph would be to first draw it on my on the picture here. So for each state, I'm going to put a vertex down, just like this. Okay, Rhode Island's really small. Okay, so for each state, I put a vertex down, and then whenever 2 states are touching, I join them with an edge. So that means Massachusetts and New Hampshire, Massachusetts and Vermont, Vermont and New Hampshire, New Hampshire and Maine, and I think that is it. Okay, and then what you should probably do is you take this graph and you can redraw it. I can redraw it nicely. So I can redraw it like this. So I've got Vermont, New Hampshire, Maine, Massachusetts, Rhode Island, and Connecticut. And now I can add the appropriate edges like this. So the graphs are exactly the same, right? It's just I used the picture of New England to help me find out what the graph should look like, and then I can redraw the graph in a nicer, more symmetric way. So this type of graph, it models how things are situated next to each other. It models how things bound each other. Okay, and this sort of thing it will come up a bit later in the course as well. So that's the end of this example, and it's the end of this video.